Welcome to this online tutorial on animal cell culture simulation models in bioprocess engineering. In this tutorial, you will learn how to develop a mechanistic or knowledge-driven simulation model for a suspension culture of animal cells. The model is built from the fundamental biological and physicochemical phenomena that govern the cell culture process. In the Bioprocess Engineering online tutorial series, I present the fundamental principles of bioprocess engineering and their industrial applications in microbial fermentation, enzymatic bioconversion, and animal cell culture processes. For more tutorials and updates, please subscribe to our YouTube channel or visit our website. Animal or mammalian cells play an increasingly important role in the biopharmaceutical industry. They can be cultivated either in suspension cultures, where cells grow freely in the culture medium, or in adherent cultures, where cells attach to a solid support such as microcarriers. Today, animal cell cultures are used to manufacture a wide range of high-value biopharmaceutical products, including recombinant glycoproteins, particularly monoclonal antibodies, viral vectors for vaccines and gene therapies, and even living cells themselves for cell-based therapies. To manufacture these biopharmaceutical products, animal cells are cultivated in a variety of bioreactors. At the laboratory scale, roller bottles, spinner flasks, and small-sized stirred reactors are widely used for cell line development and process optimization. At industrial scale, production is most commonly performed in stirred tank bioreactors, which provide the precise control of temperature, pH, dissolved oxygen, mixing, and nutrient supply required for large-scale cell cultivation. During cultivation, animal cells continuously consume essential nutrients such as glucose, amino acids, peptides, and oxygen. These substrates are metabolized to produce new cellular biomass, while cells simultaneously generate metabolites and secrete recombinant proteins. As a result, the composition of the culture medium changes continuously throughout the process. Substrate concentrations decrease, whereas biomass, metabolites, and product concentrations increase. These dynamic changes depend on many factors, including the characteristics of the cell line, the composition of the culture medium, and the operating conditions within the bioreactor. Understanding and predicting these dynamics is one of the main objectives of cell culture modeling. Simulation models are at the heart of modern bioprocess engineering. They play a key role in the digital scale-up and optimization of bioreactors. These models can be viewed as digital representations or digital twins of real bioreactors. They enable engineers to evaluate different operating conditions, optimize process performance, and explore scale-up strategies before carrying out costly laboratory, pilot scale, or industrial experiments. By reducing the number of experiments required, simulation models shorten development time, lower costs, and accelerate process optimization. In this tutorial, you will learn how to construct a dynamic simulation model for animal cell cultures. To do this, we will combine kinetic models describing cell growth, substrate consumption, metabolite production, and recombinant protein synthesis, the thermodynamic and kinetic principles governing oxygen transfer, and the mass balance equations that describe the evolution of the culture medium. Finally, we will implement the model in a spreadsheet and solve the governing equations to simulate the cell culture process. The modeling methodology will be illustrated through a case study involving a batch culture of recombinant Chinese hamster ovary, or CHO cells. These cells have been genetically engineered to produce and secrete monoclonal antibodies and represent one of the most widely used production platforms in the biopharmaceutical industry. Throughout the tutorial, we will progressively develop a mechanistic simulation model of the CHO cell culture, capable of predicting the evolution of the culture over time. During the cultivation, the concentrations of the main culture components evolve according to characteristic patterns. The concentrations of the two principal nutrients, glucose and glutamine, decrease continuously as they are consumed by the cells. The dissolved oxygen concentration follows a more complex profile, It decreases rapidly during the growth phase as the cellular oxygen demand increases, reaches a minimum, and then rises again as cell growth slows and oxygen consumption declines. The viable cell concentration initially increases slowly, then enters a phase of rapid growth, reaches a maximum, and finally decreases as cell death becomes predominant. At the same time, the dead cell concentration increases continuously. The concentrations of the major metabolic byproducts, lactate and ammonia, also increase during the culture as they are generated by cellular metabolism. Finally, the monoclonal antibody concentration increases progressively, with most of the product being accumulated during the second half of the culture, when cell growth slows but antibody production remains active. Let's begin with a brief overview of the modeling methodology commonly used in bioprocess engineering. The methodology for the modeling of animal cell cultures follows the following steps. Formulate hypotheses regarding the fundamental phenomena governing the process. Select appropriate thermodynamic and kinetic laws to describe these phenomena, particularly those related to animal cells' kinetics and oxygen transfer. Derive the model equations based on mass balance relationships for the key culture components. Solve the resulting system of equations to simulate the culture dynamics. In bioreactors, the concentrations of cells, nutrients, metabolites, and products change over time as a result of three fundamental phenomena: cellular reactions, mass transfer, and fluid flow. The primary driving force is the set of cellular reactions, which determine how cells consume substrates, grow, and produce metabolites and recombinant proteins. In addition, two important physical phenomena influence the overall culture dynamics. The first is mass transfer, particularly the transfer of oxygen from the gas phase into the liquid culture medium, where it becomes available for cell metabolism. The second is fluid flow, which governs the circulation and mixing of the culture medium within the bioreactor. These three phenomena form the foundation of bioprocess modeling and will be used throughout this tutorial to develop a dynamic simulation model. If you would like a more detailed explanation of these concepts, please refer to the tutorial, What Governs Animal Cell Culture in Bioreactors. After identifying the fundamental phenomena that govern an animal cell culture bioreactor, the next step is to develop the mathematical equations that describe how the concentrations of the different culture components change over time. This modeling approach is based on the modeling triangle, a fundamental framework in bioprocess engineering. It combines material balance equations, which are derived from the principle of mass conservation, with the thermodynamic and kinetic laws that describe the underlying physical and biochemical processes. Together, these equations form a dynamic simulation model capable of predicting the behavior of the cell culture over time. Now that we have established the modeling framework, let's begin constructing the simulation model. Our first step is to select the kinetic equations that describe cell growth and metabolism in the bioreactor. The required kinetic laws must predict the specific rates of the different cellular processes as functions of the culture environment. Specific rates are typically expressed per million viable cells. The first group of kinetic variables is the specific substrate consumption rates, expressed in moles consumed per million cells per hour. Typical examples are QGLC for glucose, QGLN for glutamine, and QO2 for oxygen. Next are the specific cell growth rate, mu, and the specific cell death rate, KD, both expressed in reciprocal hours. We then define the specific metabolite production rates, expressed in moles produced per million cells per hour. Examples include QLAC for lactate and QNH4 for ammonia. Finally, the specific protein production rate, QP, represents the amount of recombinant protein produced per million cells per hour. The specific cellular rates are not constant. They depend on the local environment experienced by the cells, which changes continuously throughout the culture. The first group of influencing factors is the availability of nutrients in the culture medium. These include glucose, glutamine, other amino acids, and dissolved oxygen. As these nutrients are consumed, their concentrations decrease, affecting cellular metabolism and growth. The second group consists of metabolic byproducts, particularly lactate and ammonia. As these compounds accumulate, they can inhibit cell growth, reduce cell viability, and decrease protein productivity. Finally, the specific rates are also affected by physicochemical conditions, especially temperature and pH, which influence both cellular activity and metabolic pathways. For a more comprehensive introduction to animal cell culture kinetics, please refer to the tutorial Animal Cell Kinetics in Bioreactors. The cell growth kinetics are characterized by a maximum specific growth rate, mu max, which represents the growth rate under ideal conditions. That is, when nutrients are abundant and no inhibitory metabolites are present. In this tutorial, we will use a kinetic model for CHO cell cultures, in which the specific growth rate mu is obtained by multiplying mu max by 4 correction factors that account for nutrient limitations and metabolite inhibition. The first correction factor describes glucose limitation. It follows the classical Monod equation and depends on the glucose concentration, GLC divided by KGLC plus GLC. The second correction factor describes glutamine limitation. It has the same monod form and depends on the glutamine concentration, GLN divided by KGLN plus GLN. The third correction factor accounts for lactate inhibition. It is expressed as 1 minus lac divided by lac max raised to the power of 2. Here, lac max is the lactate concentration at which cell growth completely ceases. Finally, the fourth correction factor represents ammonia inhibition. It has the same mathematical form, 1 minus NH4 divided by NH4 max squared. Here, NH4 max is the ammonia concentration at which growth stops completely. By combining these 4 factors, the model captures how nutrient depletion and the accumulation of inhibitory metabolites progressively reduce the specific growth rate during the culture. The specific cell death rate, KD, expressed in reciprocal hours, is modeled as a function of the concentrations of the 2 main inhibitory metabolites, lactate and ammonia. The model is characterized by a minimum specific death rate, KD0, which represents the natural cell death rate when the concentrations of lactate and ammonia are negligible. In this tutorial, we will use a kinetic expression in which the specific death rate is obtained by multiplying KD0 by 2 acceleration factors that account for the effects of metabolite accumulation. The first factor describes the effect of lactate. It increases exponentially with the lactate concentration and is expressed as exponential, lac divided by KD lac. The second factor describes the effect of ammonia. It also increases exponentially with the ammonia concentration and is expressed as exponential, NH4, divided by KD-NH4. By combining these 2 factors, the model captures how the accumulation of lactate and ammonia progressively accelerates cell death during the culture. The kinetic expressions for substrate consumption describe how cells use nutrients to support both cell growth and recombinant protein production. For glucose, the specific glucose consumption rate, QGLC, is expressed as the sum of 2 contributions. The first term is proportional to the specific growth rate mu and represents the glucose required for biomass formation. The proportionality constant YGLC over X is the stoichiometric coefficient, expressed as the number of moles of glucose consumed per million cells produced. The second term is proportional to the specific protein production rate, QP, and represents the glucose required for recombinant protein synthesis. The corresponding stoichiometric coefficient YGLC over P is expressed as the number of moles of glucose consumed per gram of recombinant protein produced. In this tutorial, we neglect the additional glucose consumption associated with cellular maintenance, an assumption that is generally appropriate for batch cultures. The same modeling approach is applied to the other key substrates. Similar kinetic expressions are used for the specific glutamine consumption rate QGLN and the specific oxygen consumption rate QO2, each including contributions from cell growth and recombinant protein production. The production of metabolic byproducts is closely linked to substrate consumption. Lactate is produced primarily through glucose metabolism. Its specific production rate, QLAC, is assumed to be directly proportional to the specific glucose consumption rate, QGLC. The proportionality constant, YLAC over GLC, is the stoichiometric yield coefficient. It represents the number of moles of lactate produced for each mole of glucose consumed. A similar approach is used to describe ammonia production, which originates mainly from glutamine metabolism. The specific ammonia production rate, QNH4, is assumed to be directly proportional to the specific glutamine consumption rate, QGLN. The corresponding stoichiometric yield coefficient, YNH4 over GLN, represents the number of moles of ammonia produced per mole of glutamine consumed. These simple stoichiometric relationships provide an effective way to couple metabolite production directly to substrate utilization in the simulation model. Modeling recombinant protein production is generally more challenging than modeling substrate consumption or metabolite formation. Unlike these processes, protein production is not always directly coupled to cell growth. During the early exponential phase, cells devote most of their resources to proliferation, and recombinant protein production is often relatively low. The highest production rates are frequently observed later in the culture, when cell growth slows or even comes to a halt. The protein production kinetics are characterized by a maximum specific production rate, which represents the production rate under ideal conditions. That is, when nutrients are abundant and no inhibitory compounds are present. In this tutorial, we will use a kinetic model in which the specific antibody production rate, QAB, is obtained by multiplying QAB max by 6 correction factors that account for nutrient availability, inhibition by metabolites and product accumulation, and the influence of the cell growth rate. The first correction factor describes glucose limitation and follows the classical Monod equation. The second correction factor describes glutamine limitation using the same Monod expression. The third correction factor accounts for lactate inhibition. It decreases protein production as the lactate concentration approaches its maximum inhibitory value. The fourth correction factor represents ammonia inhibition with the same mathematical form. The fifth correction factor accounts for product inhibition. As recombinant antibodies accumulate in the culture medium, they progressively reduce the rate of further protein production. Finally, the sixth correction factor accounts for the influence of the cell growth rate. As the specific growth rate increases, cells allocate more resources to proliferation and less to recombinant protein synthesis. Consequently, the specific protein production rate decreases. By combining these 6 correction factors, the model captures how nutrient depletion, metabolite accumulation, product inhibition, and cell physiology interact to determine the specific recombinant protein production rate throughout the culture. Although the mathematical structure of the kinetic model is remarkably consistent across CHO cell lines, the values of the kinetic parameters can differ significantly. The kinetic equations themselves are generally transferable. Most CHO cell lines can be described using the same families of kinetic equations for growth, substrate consumption, metabolite formation, cell death, and product synthesis. However, the parameter values vary considerably. The kinetic constants depend on the specific cell clone, the expression system, the adaptation history, and the culture conditions. Therefore, when applying the model to a new CHO cell line, there is usually no need to change the model structure. Instead, the same kinetic equations are retained, and only the kinetic parameters are re-estimated from experimental data for the new clone. Our next step in building the cell culture model is to select the equations that describe 2 key physical phenomena: the transfer of oxygen from the gas phase into the culture medium, and the influence of fluid flow and mixing within the bioreactor. The time variations of most substrates and products in a cell culture are governed primarily by cellular metabolic activity. However, the situation is different for the gaseous compounds, oxygen and carbon dioxide. In addition to being consumed or produced by the cells, their dissolved concentrations are strongly influenced by gas-liquid mass transfer. Because oxygen and carbon dioxide have relatively low solubilities in culture media, the rate at which they are transferred between the gas and liquid phases becomes a key factor controlling their concentrations. This mass transfer rate is, in turn, strongly affected by the hydrodynamics inside the bioreactor, particularly the medium circulation generated by the mixing impellers. In this tutorial, we will focus on modeling oxygen transfer, which is essential for maintaining adequate oxygen supply to the cells. The transport and fate of carbon dioxide in bioreactors will be covered in a future tutorial. Animal cell bioreactors are continuously aerated to supply the oxygen required for cellular metabolism. The oxygen transfer process can be divided into three stages. First, oxygen is introduced into the bioreactor through the aeration system. Second, oxygen is transferred from the gas bubbles into the liquid culture medium, where it dissolves. Finally, the cells consume the dissolved oxygen to support respiration, growth, and recombinant protein production. What is the thermodynamic law for oxygen solubility in water? Oxygen solubility refers to the concentration of dissolved oxygen in water at equilibrium with the oxygen partial pressure in the air. It represents the maximum amount of oxygen that can dissolve in water at a given temperature and atmospheric oxygen content. Oxygen solubility is described by Henry's law, which governs the equilibrium between oxygen and air and its dissolved form in water. The oxygen solubility O2 star, expressed in gram oxygen per liter, is calculated as the partial pressure PO2 in atmosphere, divided by the Henry's constant KO2 in atmosphere liter per gram. The partial pressure PO2 of oxygen in air is the product of the oxygen molar fraction YO2 by the total pressure. At 37 degrees Celsius and 1 atmosphere of air, the solubility of oxygen in water is near 0.2 millimoles per liter, or 7.3 milligrams per liter. What is the kinetic law for the oxygen transfer rate? Oxygen transfer between the air and the liquid medium is primarily limited by the transfer of oxygen from the first liquid layer at the air-liquid interface, which is saturated with oxygen, to the bulk liquid medium where the dissolved oxygen concentration is O2L. The rate of oxygen transfer, JO2, in grams of oxygen per hour is described by the following mass transfer law, accounting for diffusion and convection at the air-liquid interface. JO2 equals SKL, O2 star minus O2L, where S is the transfer surface area between the air and liquid solution in square meters. KL is the oxygen mass transfer coefficient in the liquid phase solution in meter per second. The oxygen concentration difference, O2 star minus O2L, serves as the driving force for the oxygen transfer. One generally introduces the volumetric interfacial surface area A in square meters per cubic meter between the air and the solution, defined as the transfer surface area S divided by the medium volume V. The rate of oxygen transfer, JO2, is then expressed as JO2 equals KLA, O2 star minus O2L, V. The product KLA in our -1 is the volumetric oxygen transfer coefficient between the air and the liquid solution. It characterizes the oxygen transfer capacity of the aeration system. What governs the oxygen transfer capacity KLA? The oxygen transfer coefficient KLA depends primarily on the fluid flow or agitation within the fermenter and on the aeration rate. 1. Influence of agitation. The first major factor affecting KLA is the medium agitation power, or mixing intensity. The mechanical power consumption for tank agitation, PA in watts, is typically estimated using the following relationship: PA equals NP rho n to the power 3, dA to the power 5, where NP is the impeller power number, rho is the fluid density in kilogram per cubic meter, n is the impeller rotational speed in second minus 1, and dA is the impeller diameter in meter. According to this relation, PA is directly proportional to the fluid density rho, increases with the cube of the impeller speed n, and increases with the fifth power of the impeller diameter dA. It is directly proportional to the power number NP, which depends on the impeller geometry. 2. Influence of aeration. The airflow rate QA introduced into the fermenter, typically in liters per minute, is another key determinant of KLA. More precisely, KLA depends on the gas superficial velocity UG in meter per second, defined as UG equals QA over omega, where omega is the cross-sectional area of the fermenter in square meters. Higher gas flow rates, and thus higher UG, enhance gas-liquid interfacial area and mixing, leading to improved oxygen transfer efficiency. In aerated bioreactors, the volumetric oxygen transfer coefficient, KLA, increases with both the agitation power and the aeration rate. This relationship is commonly described by an empirical correlation of the form KLA equals A multiplied by the volumetric agitation power raised to the power m, multiplied by the superficial gas velocity raised to the power n. In this equation, the volumetric agitation power represents the mechanical energy supplied by the impeller per unit reactor volume, while the superficial gas velocity characterizes the aeration rate. The constants A, m, and n are empirical parameters that depend on the bioreactor geometry, the impeller design, and the reactor scale. Typical values are A equals 0.002, m equals 0.7, and n equals 0.3. The graph illustrates the corresponding variation of KLA as a function of the impeller rotation speed, expressed in revolutions per minute, and the aeration rate, expressed in VVM, or volumes of air per volume of liquid per minute. As expected, increasing either the agitation speed or the airflow rate enhances oxygen transfer. For the conditions considered here, the calculated KLA increases from approximately 3 to 13 per hour, as both operating parameters are increased. Having established the kinetic laws governing cell growth, metabolism, and oxygen transfer, we can now formulate the mass balance equations for the different components of the cell culture. These equations describe how their concentrations change over time during the cultivation process. For each component in the cell culture, the instantaneous mass balance expresses the fundamental principle of mass conservation at every moment in time. It consists of 4 terms: the inlet rate, representing the transport of the component from outside into the bioreactor; the outlet rate, representing its transport from the bioreactor to the outside; the biotransformation rate, which can be a production rate for a product or a consumption rate for a substrate; and finally, the internal variation rate, which represents the rate of change of the component's mass inside the bioreactor. The instantaneous mass balance is therefore written as inlet rate plus or minus production rate equals outlet rate plus variation rate. The production rate term is positive for components produced by the cells, such as biomass, metabolites, or the recombinant protein, and negative for substrates that are consumed during cell growth and metabolism. The biotransformation rates introduced in the instantaneous balances represent the overall transformation rates taking place within the entire bioreactor. Depending on the component considered, these rates are expressed either in cells per hour or in moles per hour. For our CHO cell culture, we consider several biotransformation rates. First, the cell production rate Rx and the cell death rate Rd. Then, the consumption rates of glucose RGLC, glutamine RGLN, and oxygen RO2. And finally, the production rates of lactate RLAC, ammonia RNH4, and protein RP. If the bioreactor is well stirred, the concentrations can be considered uniform throughout the culture medium. We can then introduce the volumetric biotransformation rates, expressed either in cells per liter per hour or in moles per liter per hour. A volumetric rate is simply the corresponding global rate divided by the volume of culture medium inside the bioreactor. For our CHO cell culture, we therefore define the volumetric cell production rate, Rx third, and death rate, Rd third. The volumetric consumption rates of glucose, RGLC third, of glutamine, RGLN third, of oxygen, RO2 third, the volumetric production rates of lactate, RLAC third, ammonia, RNH4 third, and proteins, RP third. These volumetric rates are particularly important in bioreactor analysis because they characterize the intensity of the biological activity per unit volume of culture. Most importantly, they directly govern the rates of change of the different component concentrations over time during the culture. During the culture, the volumetric biotransformation rates are directly related to the corresponding cell-specific rates. For each culture component, the volumetric rate is equal to the specific cellular rate multiplied by the viable cell concentration XV. This relationship highlights an important feature of cell culture processes. As the viable cell concentration increases, the overall intensity of the culture per unit volume also increases. In other words, even if the activity of each individual cell remains unchanged, a higher concentration of viable cells leads to higher volumetric consumption and production rates. Let us begin with the mass balances for the viable and dead cells. In a batch culture, there are no inlet or outlet streams. As a result, the general mass balance simplifies to biotransformation rate equals variation rate. For viable cells, two biological processes must be considered. Cells are generated by cell growth and removed by cell death. The instantaneous balance on the bioreactor, expressed in cells per hour, is therefore written as cell growth rate, Rx, minus cell death rate, Rd, equals the rate of change of the viable cell number, dNV over dt. Introducing the culture volume, V, and the corresponding volumetric rates, the balance becomes volumetric growth rate, Rx third, V, minus volumetric cell death rate, Rd third, V equals V dx V over dt. Since the culture volume remains constant during the batch process, we can divide by V, giving the differential equation for the viable cell concentration, dxV over dt equals Rx third minus Rd third. Expressing volumetric rates as the product of specific rates and viable cell concentration, xV, the differential equation becomes dxV over dt equals mu xV minus k dxV. The balance for dead cells is simpler. Dead cells are generated by cell death, and in the absence of cell lysis, they remain in the bioreactor. The instantaneous balance is therefore cell death rate Rd equals the rate of change of the dead cell number, dNd over dt. Expressing the balance in terms of volumetric rate gives volumetric cell death rate, Rd third, V equals V dxd over dt. Again, since the culture volume is constant, we obtain dxd over dt equals Rd third, or in terms of the specific death rate, dxd over dt equals k dxv. We now apply the same approach to glucose, which is consumed by the cells during growth and metabolism. In a batch culture, the instantaneous mass balance for glucose, expressed in moles per hour, is written as minus glucose consumption rate, RGLC, is equal to the rate of variation of the glucose amount in the bioreactor D, mglc over dt. Introducing the culture volume, V, and the corresponding volumetric rate, the balance becomes minus volumetric glucose consumption rate, RGLC third, V equals V dglc over dt. Since the culture volume is constant, we obtain dglc over dt equals minus RGLC third, Or in terms of the specific glucose consumption rate, dGLC over dt equals minus qGLC xV. The mass balance for glutamine is slightly more complex than that for glucose, because glutamine is not only consumed by the cells, but also undergoes spontaneous decomposition in the culture medium. The instantaneous mass balance expressed in moles of glutamine per hour is therefore written as minus glutamine consumption rate, RGLN, minus glutamine decomposition rate, RDGLN, equals rate of variation of glutamine amount, dmGLN over dt. Introducing the culture volume, V, and the corresponding volumetric rate, the balance becomes minus volumetric glutamine consumption rate, RGLN, third, V, minus RDGLN, third, V, equals V dGLN over dt. Since the culture volume is constant, we obtain dGLN over dt equals minus RGLN, third minus RDGLN, third. Introducing the specific glutamine consumption rate, qGLN, and assuming that glutamine decomposition follows first-order kinetics with a decomposition rate constant, kdGLN, the balance becomes dGLN over dt equals minus qGLN xV minus kdGLN GLN. A similar approach is applied to the produced metabolite lactate. The instantaneous mass balance states that the lactate production rate, R-lac, is equal to the rate of variation of lactate in the bioreactor, dm-lac over dt. Introducing the corresponding volumetric rate, the balance becomes volumetric lactate production rate, R-lac third, V equals V d-lac over dt. Simplifying by the volume V leads to the differential equation describing the time variation of the lactate concentration, d-lac over dt equals R-lac third. Or in terms of the specific lactate production rate, d-lac over dt equals q-lac xv. The ammonia balance is slightly more complex because ammonia is produced through two different mechanisms. First, it is generated by the metabolism of the viable cells. Second, it is released by the spontaneous decomposition of glutamine in the culture medium. Since 1 mole of glutamine decomposition produces 1 mole of ammonia, the instantaneous balance in moles per hour is written as production rate of ammonia, RNH4, plus production rate from glutamine decomposition, RDGLN, equals variation rate of ammonia in the bioreactor, dmNH4 over dt. Introducing the corresponding volumetric rates, the balance becomes volumetric ammonia production rate, RNH4 third, V plus RDGLN third, V equals V dNH4 over dt. Simplifying by the volume V leads to the differential equation, describing the time variation of the ammonia concentration, dNH4 over dt equals RNH4 third plus RDGLN third. Or in terms of the specific ammonia production rate, dNH4 over dt equals QNH4 xV plus KDGLN GLN. The same approach is applied to the secreted antibodies. Since antibodies accumulate in the culture medium and are neither consumed nor degraded in this model, the instantaneous balance is production rate of antibodies, RAB, equals antibodies variation rate, dMAB over dt. Introducing the volumetric antibody production rate, RAB third, the balance yields the differential equation for the antibody concentration, DAB over dt equals RAB third. Or in terms of the specific antibody production rate, DAB over dt equals QAB xV. The oxygen balance is more complex than the previous mass balances because oxygen is continuously supplied to the culture through aeration. To determine the time-dependent variation of the dissolved oxygen concentration, the oxygen balance is formulated for the liquid phase of the bioreactor. Oxygen is continuously transferred from the gas phase into the liquid at the transfer rate, JO2, while the cells simultaneously consume oxygen at the rate, RO2. The instantaneous oxygen balance expressed in grams of oxygen per hour is JO2 minus RO2 equals dMO2 over dt. Because oxygen has a very low solubility in the culture medium, only a small amount of dissolved oxygen is stored in the liquid. As a result, the variation rate term is negligible. The oxygen balance therefore simplifies to JO2 equals RO2. This means that, throughout the culture, a quasi-steady state is established in the liquid medium. The oxygen transfer rate, JO2, matches the cellular oxygen consumption rate, RO2. The oxygen transfer rate, JO2, is expressed by its kinetic law. JO2 equals KLA O2 star minus O2L V, where O2 star is the oxygen saturation concentration and O2L is the dissolved oxygen concentration. Introducing the volumetric oxygen consumption rate, RO2 third, the balance becomes KLA O2 star minus O2L V equals RO2 third V. Rearranging this expression gives the dissolved oxygen concentration, O2L equals O2 star minus RO2 third divided by KLA, or in terms of the specific oxygen consumption rate, O2L equals O2 star minus QO2XV divided by KLA. This equation clearly shows that the dissolved oxygen concentration decreases as the cellular oxygen demand increases and increases as the oxygen transfer capacity, characterized by the volumetric mass transfer coefficient KLA, becomes larger. Now that the mass balance equations describing the time evolution of all component concentrations have been established, the next step is to solve the complete system of model equations. With the exception of dissolved oxygen, whose balance is represented by an algebraic equation, the mass balances for all culture components are differential equations. They describe how the concentration of each component changes over time as a function of the corresponding specific cellular rates. Because these specific rates depend on the composition of the culture medium, the mass balance equations must be coupled with the cellular kinetic laws, which describe how the rates vary with nutrient and metabolite concentrations. Together, these equations form a coupled system of differential equations that describes the dynamic behavior of the batch culture. To simulate the culture, this system is solved numerically using a time integration method, such as a spreadsheet-based differential equation solver. The numerical integration procedure used to solve this system is briefly outlined in the following section. Most of the model equations are differential equations that are integrated using a numerical method. The numerical integration approximates the actual solution curve by a polygonal curve made of successive points and straight-line segments. Let's consider the general differential equation describing the time variation of the concentration dC over dt equals a function of c and t. The differential equation is transformed into a finite difference equation by dividing the timescale t into incremental time steps of length delta t. The derivative dC over dt is then approximated by the ratio of the concentration variation delta c to the time step delta t, and the differential equation then becomes delta c over delta t equals a, or delta c equals a delta t. The incremental concentration variation delta c is the difference between the concentration c t plus delta t at time t plus delta t and ct at time t. The resulting finite difference equation is c t plus delta t equals ct plus at delta t. At is the slope at time t of the concentration time variation. The difference relation between the concentrations at time t and t plus delta t is used in the following way to carry out the numerical integration. The integration is started from the initial concentration C0. The slope A0 is calculated at time 0, and the concentration C1 at the following time T1 is determined by adding to C0 the concentration increment A0 delta T. At time T1, the slope A1 is then recalculated, and the concentration C2 at the following time T2 is determined as C1 plus A1 delta T. The procedure is repeated to calculate C3 and the following concentrations over the whole investigated time period. In parallel with the numerical integration of the differential equations, a final and essential task is the evaluation of the parameters used in the thermodynamic and kinetic laws of the model. How are these parameter values determined? Some parameters can be obtained from databases or from previous kinetic studies of the fermentation. The remaining unknown parameters are then identified by fitting the simulation results to experimental data, ensuring the best possible agreement between the model predictions and observed fermentation behavior. Once the parameter estimation has been completed, the model is fully defined and can be used to simulate and analyze the entire cell culture process. For this CHO cell culture, the simulated concentration profiles closely reproduce the experimental time courses of substrates, viable and dead cells, metabolites, dissolved oxygen, and antibody production throughout the batch fermentation. The model accurately captures the initial phase of rapid cell growth, followed by a gradual decline in the specific growth rate and a corresponding increase in the dead cell concentration. It also correctly predicts the continuous depletion of glucose and glutamine, as well as the characteristic dissolved oxygen profile, which decreases during the period of rapid cell growth and then increases again during the production phase as the cellular oxygen demand declines. Finally, the model reproduces the growth-associated production of lactate and ammonia, together with the predominantly non-growth-associated production and secretion of the monoclonal antibody. In the final part of this tutorial, we'll see how the knowledge-driven simulation model we have developed can be used to gain a deeper understanding of the dynamics of CHO batch cultures. In addition to predicting the time evolution of the concentrations of the different culture components, the simulation model also provides the time-dependent profiles of the volumetric rates throughout the batch culture. These volumetric rates represent the intensity of the different biological processes and directly determine how the component concentrations change over time. During the first part of the culture, all volumetric rates increase as the viable cell concentration rises. They then reach a maximum and subsequently decrease as cell growth slows down. Most volumetric rates reach their maximum at around 4 days of culture. The main exception is the volumetric cell death rate, which peaks later at around 6 days. The simulation model also provides the time-dependent profiles of the cellular-specific rates throughout the batch culture. The specific growth rate, as well as the specific rates of nutrient consumption and metabolite production, all exhibit similar trends. Apart from the initial lag phase, these rates are highest at the beginning of the culture and then gradually decline as cultivation progresses. In contrast, the specific death rate remains low during the early stages of the culture, but increases markedly after approximately 3 days. The specific antibody production rate follows a different pattern. It remains very low during the first 3 days, then increases steadily to reach a maximum after about 5 days, before declining rapidly during the final stage of the culture. The simulation model can be further used to identify the factors responsible for the observed temporal variations in cell-specific rates, particularly the rates of cell growth, cell death, and antibody production. The specific growth rate is modeled as the product of the maximum specific growth rate and 4 correction factors that account for glucose limitation, glutamine limitation, lactate inhibition, and ammonia inhibition. The simulation model calculates each of these 4 correction factors throughout the batch culture. When plotted as a function of time, they reveal how the contribution of each mechanism to growth changes during cultivation. All 4 factors gradually decrease as the culture progresses, reflecting the combined effects of nutrient depletion and metabolite accumulation. During the final stage of the batch culture, lactate exerts the strongest inhibitory effect on cell growth, followed by ammonia inhibition and glutamine limitation, while glucose limitation has the smallest impact. The specific cell death rate is modeled as the minimum specific death rate, multiplied by two acceleration factors that account for the effects of lactate and ammonia accumulation. The simulation calculates these two acceleration factors throughout the batch culture, allowing us to quantify the contribution of each metabolite to cell death over time. For this CHO cell culture, the influence of both lactate and ammonia increases progressively as the culture advances. However, ammonia has the stronger effect and becomes the dominant factor responsible for the increase in the cell death rate during the later stages of the culture. The specific antibody production rate is modeled as the product of the maximum specific production rate and 6 correction factors. These factors account for glucose and glutamine limitations, inhibition by lactate, ammonia, and accumulated antibodies, as well as the inhibitory effect of high cell growth rates. The simulation calculates each of these correction factors throughout the batch culture, making it possible to identify the mechanisms that limit antibody production at different stages of the process. During the first part of the culture, antibody production is strongly suppressed by the high specific growth rate of the CHO cells, as the cells primarily allocate their resources to growth rather than product synthesis. Later in the culture, as cell growth slows down, the inhibition associated with rapid growth is relieved. At this stage, ammonia and lactate become the dominant factors limiting antibody production. In summary, what have you learned in this tutorial? In this tutorial, you learned the methodology for constructing a simulation model of an animal cell culture in a bioreactor, based on an analysis of the governing physical and biological phenomena. The main steps include selecting the kinetic laws that characterize the growth and metabolism of the cell line used, applying the thermodynamic and kinetic principles that describe oxygen solubility and transfer, deriving the model equations from mass balance relationships for the culture components, finally solving the resulting system of equations to simulate the time-dependent cell culture dynamics. If interested, you can gain a deeper insight in animal cell culture's simulation models by enrolling in the online course, Digital Scale-Up and Optimization of Animal Cell Culture Bioreactors. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering, and be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.